Okay, so first of all, we have two repositories. So one is called Basics Graphics Music, and this repository include examples that start from very basic, from like essentially buttons and LED. So you just then this has the following sections. So first it has like basics like AND or multiplexer, shift register, counter, and so on, like a finite state machine first. Second, we show how students can the students can like apply their knowledge in combinational logic from the very first day by drawing graphics on the screen. And in fact, this is something I want you to do right now, because I want to test on you same stuff we will show on Maker Faire. So this is like a second thing. Third thing, then we use this with exercise with a sound, with a microphone, and with sound output. Then, in addition to it, we have exercises on microarchitecture. This is type of interview questions for students with like a FIFOs and with pipelines. And then we also have in this set of example, a very simplistic CPU, which is used to like illustrate for people idea of a CPU. So how the processor works. Oh, George,
Yep.
Okay, and so this is essentially a kind of introductory class for beginners user, except that like usually, especially when tool vendors, they do their classes like Xilinx, Altair, and so on. They usually show how to use their tools, how with mouse to set up pins, and then do exercises, but we skip all this thing. So we create a sort of virtualized and a parameterized top-level user module, which is called lab top, and which has a inputs like clocks and slow clocks. Slow clock is a clock with a frequency of 1 hertz, so one beat a second. Then we have signal for keys, switches, LEDs, 7-segment display. And we have for graphics, we have a graphics controller which gives coordinates to user module and gets back colors. So we are essentially giving user X and Y and they'll give this like color. And then we have interface with a microphone and with to generate sound. Now we essentially start with the most simple exercise. So we get we create a wire A with key 0, we create wire B with key 1, then we do XOR operation, and then we put it on LED. So basically, I want you to like assemble boards using instructions now, and then go through those exercises. So now let me make a demo what I created yesterday to show on our to Maker Faire. Just a second. Why it's not connected? It was. Oh, I may need screwdriver. Wait a second. Need get a screwdriver in the next room. Does anybody have a small screwdriver? Yes, I need a screwdriver for this. So this one is yeah, it's a small minus screwdriver. So and before we do it, let me show you demo a game in a Verilog. And today, once I show how to run examples, I actually want you to maybe create your own demos. And this can be done using very basic knowledge of Verilog. So we will go through simple examples I'm going to show on Maker Faire, and you will try to do what I expect from people on the Maker Faire. So now, in addition to a repository with example from FPGA board, we also have a repository called Homework. So System Verilog Homework. So in the System Verilog Homework, you can run it on any computer, like even like Apple Macintosh, which has like Icaro simulator. And this starts from very simple question.
Or you need a flat?
I'm really minus, but this may work. Let me connect this one.
Even though I can.
Just a second. I think this should work. Yeah, it does work. So yeah, this is. So and now we are. This graphics not only on this LED matrix, but this on HDMI, VGA, on LCD screen. So we will do graphics on LCD screen. Let me show you graphics on this board so you know like what I'm talking about. Okay, so wait. I need also cable to connect it to USB. Work. Okay, so, yeah. So here is the homework. So this example of homework. So like this starts from like the simplest possible homework that like I showed. This is a module which has inputs 4-bit D0, 4-bit D1, a selector, and a multiplexer using ternary operation. And then like I asked to make a multiplexer not between 2 pieces of data, but between 4 pieces of data. This is the simplest possible exercise you can get. And then it slowly progresses. And let me show you a type of exercises which are like already interview level. So this is a question which many students unfortunately do not answer. So suppose you have a pipeline block which computes like square root, integer square roots in like n pipeline stages. So now, so like basically this is a, like as I said, this is a pipeline block. Oh wait, let me show a picture. Yeah, this is a pipeline block. So you put some value with the valid, you wait for pipeline latency, you get the result. Okay. Now, then I ask, like I ask a person, like a first question. So suppose suppose I want you to compute formula of square root of a plus square root of b plus square root of c. So usually students do this right, so they just instantiate 3 square root block in parallel and say that let's just feed them with a, b, and c. Then put like add there and register the result of this add. So far so good. So now, if you look to waveform, so now, like if you look to the waveform, so you put A, B, C in 1 clock cycles, and you wait for n plus 1 clock cycle, and you get the result. So you can put like another. So okay, so like so far so good. But then I ask them another question. Yeah, then like I ask like other questions like what if you need to create, what if you need to compute formula? Like then I ask how to use like finite state machine to implement using only one block. So suppose you have only one square root module, so you need to use FSM to first put A, then put B, then put C, and implement everything in 3n plus 1 clock cycle. So they usually also don't have problem with this, so they create FSM and it works. Now, what students do have problem is so yeah, then I ask them, suppose you want to implement you want to implement a formula with dependencies. So let me draw it on the screen for more for more clarity. So then I ask students that suppose you want to implement formula A plus square root B plus square root C, right? And suppose this formula has to be pipelined. So you like put A, B, C, and then like after some like M clock cycles, you get result of this formula. But you also need to put on next clock cycle, you need to put like another like A1, B1, C1, and get this result after this ABC. So basically you need to process stream of data, and I think that this is actually what you need to use FPGA for, because with like Raspberry Pi to process something coming from like equipment, they get like some data and then they run some program, produce result, but your equipment probably sends you like a lot of data, and you need like every clock cycle get something and get the result. So like effectively all things in like all companies in like GPU in network companies work like that. Just in network companies we need to put stream of transfers of Ethernet packets, and in GPU it's like stream of triangles you need to like rasterize. So now when I ask students to implement formula, many start to draw something like that. So they just draw blocks. So they like draw like square root C, then they then they put here like add and put result to like, so this is C, this is B, this is A. And so they create three modules and connect them with the wires. But the problem is that this is not going to work as is, because like by the time this block produces produces square root of C, by this time B is gone long time ago. So and there is a new B for like different formula. So now basically, as like any like person with experience in industry, you all know that what we can do is that you need to simply delay data using either shift registers or FIFO or circular buffer. So, but apparently many fresh college graduates don't know it, or at least they cannot figure it out. And but usually they figure it out after some time. So some more quick thinking students figure it out in like a few minutes, but other students start saying, oh, maybe we need to put it in some register. Okay, suppose you put it in register, but if you have like 10 data coming back to back, if you have one register, data will be gone anyway. So you need to have multiple registers. So now, yeah. So now, essentially, in order to implement it, so then I usually ask whether they study like shift registers and FIFOs in school, and if like person is yes, we do. Oh yeah, we can use FIFO to delay data. You see, but frequently many students like study FIFO, and then this FIFO is sort of like vacuum in their brain. So they studied it, but they don't know how to use it. But and since essentially a lot of work, especially with the processing stream of data, is a combination of pipelines and FIFOs, we need to train students on such examples. So you see, you can use shift register by delaying data for like number of clock cycles, or you can use FIFO. So you need essentially to build such constructs for fixed latency computing with and there are like many of such constructs, especially in like GPU in fixed GPU pipeline, and in networking with processing packets. So this is like a type of examples we have in homework. So now, in order to how to run homework, so how many of you got computers? So you have Dell computer, so you can run probably example with a FPGA board right away. Yeah, on Apple, there is open source toolchain for Govin, but it's difficult to use. But you can still use do this system Verilog homework here. Then if then I believe that somebody was asking for additional computer. I have like that computer, and like you can like borrow right now some computers for today, but if you need additional computer at home, I have a couple of computers at home you can use for some time. But today I want everybody new to run exercises we are going to show on Maker Faire. So now I will test new Maker Faire. And so let me show you this example which I created yesterday. So first of all, how do we run examples? So I usually recommend people to use Visual Studio Code because this is popular. Yeah, so Visual Studio Code is a popular editor. And usually I ask to create a terminal here, but so you need to open. You need to clone a repository called Basics Graphics Music, and they have exact instructions for it. So if you go to Verilog meetup.com, you can get instructions. By the way, if I don't have your email, like I would ask you to send your email to me so that I can put you in the mailing list and send you all the necessary links. So my email is yuri@panchel.com. Yeah. Or you can just go to Verilog Meetup website and get information in there, like join like mailing group and so on. So first you are getting Basics Graphics Music repository, and this has a tree with these examples like basics, graphics, and so on. So for the graphics, we have, for example, this game with the sprites. And to run example, like usually I do open an integrated terminal, but now we need to pull a repository. So we are doing git pull to get latest examples. Okay. Okay, so now we need to run script called choose FPGA board. This is 06. Choose another FPGA board, and this script gives you a long list of boards. More frequently, I run it in a terminal together with a midnight commander, but you can do it like either way. So if you go to game, so like if you do this 06, choose another FPGA board, it gives you this long list of boards with support. And one activity of our club is to add support for like other boards. Yeah. Now this is a board. This is like 71, which is tank primer 25 KP mod hub. This is hub 75E LED matrix 64 by 64 bright. So 71. Good. And now I run script called synthesize. So I can run this script inside this thing too. So in a terminal in a Google code. So now it runs the script. It does synthesis. Oh, by the Alexis, at some moment I gave you such a LED matrix, but I think I gave it to somebody else, right? Or do you still have it? Do you still have LED matrix? Oh, excellent! If you do need it during show, but you can use it even right now. So you have a LED matrix, and there should be controller. Yes, everything is here. This is great. Yeah, that you had, because I was not sure I gave it to you or to like another person. So now we have actually two demo devices, and I want to make sure that somebody else can run it. Excellent, but this okay. So now let me show you what this thing does. So this implement game with sprites. So you see, so you have a like some like missile. You can hit it, but you need to make it slower. Yeah. So you see, this is like you can do some like graphics here, and you can create a set of examples even today to run on this thing. But same graphics can be run on a large monitor. So you will see how it looks on large monitor. Yeah, but this is kind of type of demo I want to have on next Maker Faire with the different graphics. And actually today I want some of you to try different graphics with this thing. Now now let's get one more monitor. So can you actually bring a large monitor with HDMI from there? And let's do this on HDMI, but also we can use smaller boards with LCD screen. And I want everybody today to try it on a small LCD board. It doesn't have screen. So this is one of our setup. We are kind of promoting for use for the beginners. So many universities are using like Nexus 4 boards, which cost like $350, but this setup costs just $34 like board, and even together with breadboard and other stuff, it's like no more than $50. So so such setups can be used from like starting starting people, and that's why we want to like give it especially for like school teachers. And basically, I want for all new people to try today this setup. Oh, this is connected in incorrect way. So we need to connect it in different way. Anyway, so what I want to do today, I want everybody to go through the following set of exercises, which I also plan to show on during Maker Faire. And we discussed these exercises with Natalia yesterday. And my goal of today is I want to make sure that you can not only run those exercises, but you can also modify them. This is HTML good. So don't you see it's a neat demo?
Yeah, that's a beautiful.
You can create a bunch of like moving graphics on this thing. Yeah, I also have a radiation counter with a Geiger counter. So we also will have a demo with radiation on Maker Faire. Yeah. Oh, before I forget, we also need to get now additional tickets for Maker Faire for people who plan to go there. So like specifically, like I got already ticket for Natalia and for Jorge, but we need tickets for Alexis and for Pete's girlfriend. I made for Pete, so we need to now get like 5 more tickets. And this is what we are going to do. Okay, so but first question, Alexis. So for how long can you go there? So you need a 1 day pass only, or 2 day? 2 day. Okay, so you have for all 3 day pass, so you need for 2 day. Okay, so you need 2 day, and we need one more bit. So this is 3-day. So we need Yuri because Yuri will help. Yes, Timothy, do you need a pass?
I'm not going to join.
Ah,
Skip about that.
okay, this is fine. Yeah, okay. So let me show you a type of graphics we will do there, and I want all of you to replicate this today because we need to. Okay, so first of all, so those so the goal of these exercises is to teach people who never saw FPGA in their life to modify Verilog code. Huh?
We have a test on it.
Yeah, good. So we'll test this on you. Yeah, and also the goal of today is to prepare some demo setups. So we carefully put demo setups in 2 boxes, test them today, and not touch them before Friday. So this is one of demo setup. So we also need to fix bug in the microphone, but today we are concerned only about graphics. Yeah, yeah, okay. Okay, 1 second. Okay, so this is kind of simplified setup where we have a sound output and we have microphone, and I need to put here but I will connect this to HDMI, but you can see the same thing on LCD screens here. Let me connect it to HDMI and do everything on HDMI. Okay, so I created a directory with examples called Maker Faire, and this is our first example. So this is the module header. So I will probably do simplified module header, but you can now ignore it. So now our goal is to draw a red screen, red rectangle on a screen. So how does it work? Is there any? Ah, yes, here. Let's get. Are there any better markers? This marker is actually good. Okay, so what exactly do we have with the current design? We have some design called board specific top, which board specific top which user never see, which is different for each different board. Then we have a design called lab top, and this is a design for a current lab. So all users see this code, and you can see it on the screen. Then, in parallel to laptop, there is a graphic controller, and this graphic controller can be VGA, can be HDMI, can be LCD, can be this LED matrix. So there are many different devices for graphics. Okay. Now this like device for graphics communicates with external display, and we don't want to bog novice user with what this external display is. All we want is this module gives to user two coordinates, X and Y. And user needs to implement combinational cloud, a function without side effect, which gives back to the display RGB, so color. So basically this controller module gives it here's X and Y, give us back color. Now how to draw rectangle here. So let me make this larger so that everybody, so like everybody can see on the screen, right? Like everybody can see. So basically we created so-called always block of combinational logic, and we first initialize red, green, and blue with 0. And then we put that if X is more than 100 and Y is more than 100 and X less than 150 and Y less than 150, then red is equal 30, which means that make this a color of red. So now I will run script. I can run this script here inside this code, but on second the screen on that screen it's better to show it. So now let me go to project, CD projects, basics graphic music. This is graphic music, labs. So this should be on the screen in Maker Faire, 9 Maker. And then we go to first red rectangle. Okay, so we are running, so first we do choose another FPGA board 06. We are doing this only first time. And we need to put here board 10 Nano 9 HDMI TM1638. So this is board number 50. Okay. And now we need to run script called 06, 03 synthesize. Okay. So this is connected to this HDMI display, and it's supposed to draw a red rectangle here. Does it work? Oh yeah, yeah. But this rectangle is the too weak color, so you can see it's too dark, and this is dark because in this simplified example we don't take into account the actual technology of the display. This display can support up to 8-bit per color channel. So red is from 0 to 255. Green from 0 to 155, blue from 0 to 155. So we need to modify our example. We need to put here red is equal to 55 to make it like brightest red we have, right? So now we save it and run this again. So now we are supposed to see, and also we can make this larger. So let's, while it's synthesized, let's make it not 100, but let's make it like 1000. no, this actually is a support. Yeah, see, so this is now bright red color. So now, second thing, what we are going to do, we are going to next example, which is called two rectangles. So here we have one rectangle red, and we will just just make it larger. So let's make it like 650, and let's make it like 800, and let's make rectangle green. Let's put green from, let's say, like 400, like 300 to like 700 and 500. Or let's make it like oh wait, this actually should be smaller, so this should be like 350, because we put a resolution only 640 to 480. Yeah, so now 350, 500. Okay, and let's make red maximum red, and let's make green maximum green. Okay, and let's run the script 3. Now, like you would ask, so can we see the schematics of we use in this FPGA? Yeah, so you can see that it created red rectangle and the green one, and on cross section it's yellow, because we did the components of red and green, so it combines yellow. Now, if you want to see what kind of schematics we got from this, so we have script which runs GUI. And in this GUI, if you go to schematic viewer, RTL design viewer, you can actually zoom and see what kind of schematics we get on our design. How to do zoom here? Yeah, you can do zoom this way. Okay, so this is bridge, TM, micro. Yeah, this is our laptop, so this is our module. But unfortunately, schematics in this tool is not like obviously visible. But some tools like Altera Quartus shows better schematics. But you see that synthesizer converted our code into a schematics, like into AND and OR gates and some comparators and stuff. So this is how logic looks like here. Okay, so now the question is that how to make actually. Okay, so next next thing what we can do is that we can change colors of our display with the keys. So now let's put here 255, 255, 255. So now we change the red, green, and blue, and we will make some larger rectangle. So here is a 400, and we can also make rectangles with a different width. So we can make it width is 200 or 50. Yeah, and here is fine. So we will use two keys to modify color and size of those rectangles. Okay, so let's run synthesis again. So this is introduction to combinational logic. How can you define combinational logic? So combinational logic is essentially graph of it's too dark. Yeah, it's too dark because we don't press anything. So you see, when we press key and when we press both keys, it's now yellow. When we press blue, magenta, cyan, and if you press everything, it's a white. Yeah, so so you can see it here. Yeah, now it also created green here, but this green is too dark. Is it dark because we didn't put enough? Yeah, we put green 30. So let's put green like 300. And we put plus W, so W is a width. So let's make width larger, like put like 6 and or 250. So this is key number 4. So if you put key 4, yeah. So key number 4 makes this a different size. So we need to change this to like accommodate HDMI display, because now it is written for small LCD display, which has not 8-bit per channel, but just 5-bit per channel. So now we run this thing. Yeah, so the good thing is such code is that you can study syntax of Verilog, how to write like all the constructs by creating some like interesting looking things. And some of the syntax, by the way, like a lot of university graduates do not know like a lot of syntax. Like I will show examples right now. Okay, so now it show, I still put it in dark color. Yeah, here. So, but I still put dark color, so I need to put bright. Oh, I put 300, which is more than 200, 255. So that's why it cut 8-bit and created small number. Anyway, let's do something more interesting. Now, the question is that how to make something moving. So basically, all digital logic is comprised of two type of element: combinational logic and clocked element. And for like our for Maker Faire, I am going to bring a large poster to show it. So basically, let me show this on a couple of slides. And I'm going to print large posters. This is incorrect account. So here is a basic principle of like. So first of all, this slides compares like shows place of Verilog in the computer system. So you have like microcontroller like Arduino, which has a CPU core. CPU core is designed in Verilog, and you have a program in memory, which is sequence of instructions. And just like in C, you write C code, which you convert into a sequence of instructions in the memory. And in Verilog, you create something which actually becomes mask, which becomes chip itself in a factory. And but how digital circuit design? So digital circuit has combinational cloud, which is a function without side effect, and has a state elements. And basically, any circuit can be thought of those two things. So on every clock cycle, we like update the elements. Of course, like a real chip has multiple different clocks with different frequencies and like power domains and like mixed signal analog things. But ultimately, with such thing, like even with single clock, you can implement any kind of algorithm by updating state elements. So now we will use state elements to make our things move across the screen. So first, first thing, like I said, we have this slow clock. So clock which just moves with frequency of 1 hertz, right? So now we create a counter. So this code, so this syntax means that every time on positive edge of slow clock or reset, so positive edge means that clock changes from 0 to 1. So every time clock changes from 0 to 1, if there is a reset, we set this 10-bit counter, 10-bit variable counter to 0, and otherwise we add 20 to it. So this 20 is 20, we used as 20 pixels on the screen. So we show this on our LED, so we will have a binary counter here. But also we will use it to create a moving rectangle. So we will simply add counter to our border of a rectangle, and let's put here red 255. And yeah, so we will now make a moving rectangle by just adding counter to coordinate. Let's make this rectangle larger so it's more visible. So it's 3, let's make it, actually 200 is okay. Okay, so we just, actually 150 is okay. So we just make it more intense color. So now, now you will see rectangle moving across the screen. And I need to create the same thing for this 7, for this LED matrix. Yeah. Oh, and I need to remove. Oh, this is actually a size of rectangle is increasing by 20 pixels every second. Okay. Now let's make some smooth movement. To make a smooth movement, what we do is that we create a counter. Oh, before I do this, let me show you some fancy Verilog syntax. You can learn what usually recent college graduates don't know. Majority, unless they did their like open projects. So basically, we now draw some parabolas, circles, and like other curves by some shades. Like you see, this syntax many people don't know, but this allow to. But this is like heavy used in commercial code. So just a second, didn't finish. Oh yeah. You can see here. So see, it shows with the shades, some like parabola shades and some circles, ellipses. So you can see shades of blue. Yeah, but let's go back to our example with a moving rectangle. Okay, so next thing we want to make a rectangle moving smoothly, right? Oh, yeah. So rectangle pulse. Okay, so we show here as a black box module called strobe generator. So strobe is just a control signal which lasts for one clock cycle. So like essentially, why do we need strobe? So a clock generator on this board runs with a speed of 27 megahertz. So basically, we have a 27 megahertz, but if we update coordinate with frequency 27 megahertz, it's not something useful. So we need to update, let's say, like 100 times a second. So what we do is that we have a module which gets 27 megahertz and which on like 10 or 20 times a second generate a one clock cycle pulse. And basically we are saying that this like 10 or 100 times a second, we are doing some action, like we increase coordinate to make the thing moving. Okay? So this is how this code looks like.
So if you want a timer that's 1 second, like the previous example with rectangle,
Yeah.
increase it every 1 second.
Yeah.
So is your code written specifically to the speed of that clock to calculate how often to increase it to make it change 1 second? So if you replace it with another chip that was double the clock speed, would you have to like double the time on your count?
Yes, you need, but to in order to do this for like our regular examples, we just have a parameter called clock megahertz, and for each board, this clock is different. So on some boards it's 50, on some boards it's 27, and we pass it from board specific type. So basically, we use this parameter to parameterize this strobe generator, and we are saying that we are using clock which is clock megahertz. In this case, it's at 27, and we need to generate 30 hertz, so 30 times a second. And if you are curious how this code looks like, you can see it. So you can see it here. So I have a library of frequently used components here, and strobe generator code looks like this. So inside we have as a special case when we have only like one. So we are using formula to compute period. So clock megahertz multiplied by 1000 by 1000 divided by strobe speed. So we compute how many clock cycle, how much we should count before changing the signal, and then we compute widths of our necessary counter by a logarithm of 2, and then we create always blocks. So always when positive edge of clock or negative edge of reset, and if counter is equal 0, so this syntax means all 0 bits, then I put into counter it's a constant period which we calculate in constant expression, and then I put strobe is equal 1, so I generate this one strobe. And on next clock cycle goes to 0. So basically this pulse lasts only for one clock cycle. And then we don't do anything for million, for like 10, so this is like 30, right? So 50, so this is 50 million divided by 30, it's like million something. Then we don't do anything for million something clock cycles because we don't need to. So now here, this is like all the code. So we are simply using counter and we generate strobe. Now there is difference between people who write professional code and people who do like hobby, people who do hobby frequently use this generated signal as a clock. So they use counter, and then they use bit of this counter as a clock. However, if I do such thing in Samsung, I will not be able even to check in, because software that check against this will tell Yuri error, cannot do this. Because the problem is that you cannot use bit of counter, bit of data as a clock, because bit of data is physically routed using different routing network on the chip. And if you do something like this, it may even compile and may even work on the board, but it will have timing violations. Why? Because on our chip, because it uses logic for data, on our chip, this clock will go to parts of clock in a little bit different time in picosecond, and this difference is enough to cause bugs. So basically, but like for many hobbyists, especially coming from software side, they simply don't consider it important. And because they don't consider it important, they write code like always at post age, some like counter like 7. So this is like big no in commercial code. So, but on some like hobby sites you can find it, and this just happened to work on the board, but this works by random luck. You see, and this random luck is that synthesizer sort of understands it, tries to make the best out of it, and creates some like faulty clock, but as design grows larger, it will introduce bug eventually. Just this bug doesn't appear in small design because a clock is a low frequency, design logic is not complicated, and so on. So basically, the right way to do this is, and there is a right way to do this, but people say, oh, come on, this is like not cool. So the right way to do this is to generate not clock. So just to use a regular clock, and then right here, if enable, and this enable is our strobe which we generate. So like basically this enable is our strobe. So just like once every number of clock cycles, we are doing some action begin. But like like hobby designs, they don't want to have this extra if enable. Now there are cases when you don't want to put this extra if enable. And these cases is that if you have a commercial CPU core, which may run on like a gigahertz frequency, and you want for your research purpose to run it with 1 hertz frequency, so to run it step by step, right? So in this case, probably timing doesn't matter, but if you still care, what you can do is that you can get this clock generated from the counter and put it through special magic black box which exists for all FPGA vendors. With Xilinx it's called buff G, with Altera it's called global, with Govin it's also called buff G, and you put here this like dirty clock and it produces clean clock, which is routed through proper, but those are some like small details, but we have to use it because we do have slow CPU example. Yeah.
Is that taking a signal from a hardware clock? Is that what you're saying?
This is happened when we generate clock from data. but this clock is coming not from a quartz generator, but when we use counter to divide our clock. So we have initial clock 50 megahertz, and we want to make clock of like, let's say like 1 megahertz. Or no, like with 1 megahertz we can use PLL, which is another trick. But if you want to have clock like kilohertz, with kilohertz you cannot use PLL, so people use counters to divide. But generally, this appears on many websites, and this is one of those cases that when you read it on many websites, it doesn't mean that this is correct. You see, yeah, I shouldn't probably go too deeply into this. So now we have a signal which become once 30 times a second. Now all we need to make a moving object, all we need to do is to add this to our coordinates. Okay, so this is our strobe generated, generates the signal. Then what we do is that we create a counter. And in this case, we are saying that if pulse, so if this strobe is true, then we increment counter. Okay. And once we increment counter, what we do is that we add our this counter to like our coordinate, and we create a rectangle which is smoothly moving on the screen. But let's just make it brighter. Let's make it not 30 but 255. Okay. So now okay, so now if you synthesize this thing,
Yuri, and where is the part which clears out the screen? Because, like, yeah, we will calculate coordinates, right? But like how the previous drawing is cleared out.
Previous drawing does not exist because we don't have frame buffer. So basically, we don't have any memory here. So we just do this on the fly. So basically, on the fly, our controller, like HDMI controller, gives us here is X and Y. Give us back colors. So we are creating RGB, and this thing is sending this to display, and display just accepts like a stream of such data and display it on the screen. So display internally may have its own memory, but we don't care. We don't have memory. We just calculate color of a current dot, of current X and Y. By computing it, we create this moving thing. So we don't need to clean everything. It's clean by default. Yeah. So yeah, it's it's clean. It's clean here because by default we put that red, green, and blue is equal 0. So by default it's black, and otherwise, yeah. See now it's moving across the screen. Next, we want to do what? We want to we want to move it. We want to move two things on the screen with different speed. So this just means that we use counter multiplied by 2. Yeah. Okay. So. And by the way, we can create not like rectangle, we can create circle. So how to create circle? All you have to do to create circle, you need to do that x minus. Let's actually put it here. So red 255. 155. So now, in order to draw a blue So in order to draw a blue circle on the screen, what we do is that we do x minus 100. Let's make it static. So in a Verilog, in system Verilog operation, square is this, but you also can multiply by 6 minus 100. So if x minus 100 power 2 or multiply x minus 100 plus same thing about y minus 200 multiplied by y minus 200. If it's less than 100 multiply 100, then we put blue is equal to 55. So this is how we draw a blue circle. Okay. Now let's synthesize it. And by the way, you can see here on LED indicators a binary counter. So we actually put a counter which increments 30 times a second. Jorge, Alexis, you will need to do the same thing I'm doing now on Maker Faire, okay, in Spanish. Okay. Oh, you see? So this is our circle, and this is moving rectangles. So now we are one step from writing a computer game. Okay. All you need to do in computer game is you need to add keys here. You need to put yeah. So this is actually next thing. So now here we have strobe, here we have counter, red, green. Yeah, but here also I put 7-segment display to show this in 7-segment, but let's actually skip it. And let's do this using key. So now we're actually close to writing a computer game by using key with X and Y. So you see, we create two counters. One counter is for DX and another counter is for DY. And now, if we press one key, we increment counter, and then we press another key, we decrement counter. Okay. So now we put here red. Let's make red brighter to 155. And let's make green brighter to 155. And let's actually get here. Let's actually get here our I think this was in which one? It was 5. So what lab we created? We created it here. So let's actually move. Let's actually create a moving circle. Oh, sorry. Let's actually create moving circle here. So, but let's actually make the circuit moving with dx. and dy. Yeah, so what we do is that we put x plus dx, x plus dx, and in terms of y, let's put 100 plus dy. This will be too much complicated. So let's put dy. Let's put dy. Yeah, so this is my new theory, is to teach Verilog syntax by writing games on the screen. Yeah, but because you see many people in universities, they first do exercises with buttons and LED, and then they connect some like sensors, and then they put CPU. But I don't see much value in a student to like instantiate Xilinx microblaze CPU, because he it's like too much complicated. Oh, you see, let's press it. You see, so I press it this way, and I press buttons, and they move in different directions. Yeah, but that one I need probably to change where it originates. Yeah, you see, so now you just press buttons, and then you see when pieces collide, and you have a computer game, essentially.
Where are you getting the final x and y values for the screen? So let's say as the squares are getting out of this
Yeah. Yeah. This is a good question. So basically, all this module is parameterized by screen width and screen height. So what you do is like, let's say you write so you can write here that the dy has some limits. So you can put here something like if something like else if dx is equal screen width divided by 2, so you cannot do more dx more than half screen. And so and you can put like code like this. So you see, you can put like dx screen width, and you can put same thing as a screen height, but and otherwise you just keep the same dx as it was before. So because this is stored in registers in the D flip-flops, so dy is equal screen height divided by 2. Okay, so let's synthesize this one and see what happens. So now this will move. Oh, but also it adds counters. So we need to limit counters. So this has like fixed movement plus movement because of our keys. So if you like eliminate counter from there, you can move only up to a border. So see, if I press, yeah, so you see, it actually reached counter. Yeah, so you see, you can control this thing. Yeah. Okay, so what I recommend to do right now, I recommend just everybody either uses their own computer or borrows computer, and we just everybody run those examples with the boards we are going to use as a demo. So now let me show you how to connect LCD screens. But make sure not to misplace and not to mix anything, because today I want to prepare boxes with demos. So if everything will be in chaos, you have to spend 3 hours sorting it out, you know. So everything you're getting should be put in the same box. So basically, let me show how to connect this. How to connect this screen. So you just get this screen, and you connect it here, and then you can do everything from the screen. Yeah, this wrong idea of putting it. Put it here. So you need with finger to put this thing up and then insert screen and put it down. Ah. So everything here will be an LCD screen, and then just to connect it to computer. Yeah. And this has to be put in different way.
No, that was working.
Huh? 1 second.
We can manage that with that movie.
I understand. But we need to prepare demo today. It's not because do this today is much better than to do this in a hurry on the floor on Friday. With like 100 school children coming and watching this. So basically all demos should be put in order and not in chaotic way today. This microphone, bugging microphone should be fixed. Okay, anyway, I will take care of this later. Okay, so you just we have to do more space here. We have to put more space. Okay. Anyway, so you can just connect. But you need to do git pull first. Okay. So here's one. So you have it. So you have okay. So but do you have Apple Macintosh? Yeah, but on Apple Macintosh it's not going to work. So now yeah, so you can actually try with the Jorge. So Jorge will show how to run examples. So you have everything. So you have everything. Yeah. Okay.
It's 50. Which board number?
Numbers, you need to look git cool and then read don't use numbers as a guide. Numbers are changing every day. So just this board, no, make a menu.
How I make a menu?
Wait, git, yeah, okay.
Yeah, it's already done.
So go to lab.
Where?
Okay, so you're now inside basics, basics. If you want to go to that specific thing, you go to maker fair and then you go, let's say, here you can start from the first lab. You do right mouse button and then you put open in integrated terminal. So it will now open in a PowerShell, but you can also open in a Bash shell if you want. But if you open this, so what you do is that you just press Bash and then synthesize for FPGAs. And, 0C. Yeah. So 0C synthesize for FPGA. So you choose board already, right?
Okay.
But did you choose the board?
No, not yet.
Okay. So what you do is that here 06, or you can use a Bash terminal, which might be a better idea, but this is fine. So you choose another FPGA board, and then for this particular board,
No such fine right here.
it's a what?
Yeah, we need to use the Bash.
No, wait, this should not be there. It's a bug. It's a new bug. I need to fix it right away. It's somebody was using DOS engines.
Yeah.
So we are testing this now. So you shouldn't walk around anything. We need to fix it now. Not walk around. No walk around. I will fix it. You do pull right now because we are testing now. We are not trying to get through. We are testing so that other people don't make this mistake. Okay, so looks like what happened is whoever was modifying this thing accidentally put, or maybe you have such settings in your Git.
That maybe.
So maybe your Git converts this into Windows when you install Git. So when you install Git, did you try to mess with options?
No, I as well.
You put everything by default. You put everything by default. We need to know like investigate why this happened, because if this happened with you, this happened with other people. So let's investigate. Let's not work around it. We need to fix it right now. So this happened in this red rectangle, right? So let's see. So and this happened in 06. So does it show? No, it shows 0A, so it doesn't have 0D. Okay, now Unix, DOS to Unix. Git checkout. Ah, Yeah, you can try in the meantime to run a bash terminal, whether it works in bash terminal. But then we need to fix it anyway. Dash n dot. Okay, let me actually check something on your computer. Okay, let me see. This is.
Yeah, I open a bash here.
So you are saying that if you okay, so you are saying that if you go to labs, and if you go to Maker Faire, so if you do 0, 6, oh, not 0, 6, simply 6. Oh, maybe it didn't work there because you put 0, 6. No, okay, anyway. Oh yeah. You need to, okay. So now 0, 6 choose another FPGA boards. Okay, so in bash terminal it's working. Now the question is why it doesn't work in regular. Do you have do you have a Windows subsystem Linux?
Yep. Yeah.
Maybe this is the reason.
Hmm.
But I thought that I detect Windows subsystem Linux and just produce a message about it. So which bash is it's trying to run? Which bash?
Which is not recognized.
Is that because you that time it's because you use PowerShell, right? There's no which in PowerShell. I don't think.
No. PowerShell is supposed to run Git from bash, and then Git from bash is supposed to interpret those scripts. If this doesn't matter, it means that you have a bug. Or there is something weird on this computer you need to like investigate. We cannot just leave it as is because then this happen like
I have seen the Git bash.
No. This is trying to work around. We need to solve problem. We cannot work around. So we need to see it in path. We need to like investigate what bash executable is trying to run. Okay, I will investigate it with you like after we finish this. But let's go back to bash shell. Okay, so here we need to select board, which is called Tank Nano 9K LCD 480 272 TM 1638. So this is number 53. This is Tank Nano 9K LCD 480 272 TM 16, because this is TM 1638 and this is here.
Is it worth putting that in the README on the repo?
Huh?
Is it worth putting that in the README on the repo?
In README, yes, this we have instructions for it.
Oh,
So you have a PDF instruction. In fact, I printed those instructions, so I need to just give you instruction to follow. Yeah. So what I'm doing now is not correct. I need to give you instruction, and then you need to follow instruction. And now we just run it. Yeah. So now it's running. Okay. Now let me give instructions. Oh, I think I left it at home. Yeah, so now you have it here like on the screen. Okay, so now try to play with those examples and modify them. Okay, so Yeah. So okay. That's fine. So yeah, you can just go to like Verilog meetup.com and get the whole information there. Yeah. So what I recommend to do is if you want to get a skill in Verilog, I recommend you to do homework examples. Just do them one by one using carousel. And this is especially if you want to produce like a stream of data from equipment for like analysis, because you need to learn like micro architecture, like examples with such like processing. And if you instead get books like programming FPGA for beginners,
Yeah.
So, well, when you click on that down arrow there.
yeah, but most of them teach you up to how to do some finite state machine and integrate with sensors, but they don't teach you how to process data in high performance. So, but to learn, you need to go through this homework and then do it. Okay, that's fine. Okay, yes. Yeah. Okay, so I think like I offered you instead of like output, use one of those opportunities. Yeah. So I can give you that computer after he stop using it because I have some extra code. But right now you can try this one. Yeah. Okay. Now, so what happened? Yeah, I can give you bootable USB drive. Yeah, but we need to also, so now I need, before I forget to give you a ticket. So how many tickets? So I have some 1 day inexpensive tickets. So how many do you need for 1 day?
83. You can be there Friday.
I will be there for 3 days. You will be there all time. Okay, but are you going to stay in Vallejo or just to drive from here?
People probably drive up and stay.
And stay there. Yeah, okay, this is fine. So let me get maximum tickets and distribute. Okay, so how long can you go there? Can you go there? Make your fair. It's yes, Vallejo. Huh?
1 day. 1 day.
It's from Friday to Sunday this week.
Oh, no, we're not doing it, but I can help you with that.
Okay, but you cannot go there, so you don't need tickets.
No.
Okay, so Pete need tickets, so like Alexis need tickets. So what about you?
I can do it, yeah.
Huh? For how long?
So you say 3 days?
Yeah, 3 days. If you're going to stay there for 3 days, but you need to stay there in the hotel in this case, because it's long drive from here. Do you want to drive every day?
So Valeria, it's like what, a couple of
Yeah, so try to check. Okay, Natalia already has ticket. Okay, so what? Timothy cannot make it, so we need to have a ticket. So I will get tickets right now. Yeah. Huh? Yeah, that's fine. Okay. Okay. So, speaking of you, so what is your plan? Like I can actually show you this UVM like example, or what what is your plan? So what do you want to do? So tell.
So you showed me an AXI code last time.
Yeah,
You said you
yeah.
wanted it.
So do you have a link for it? Okay, let me give you. So if you can give me your email, like I have your email already, right? Yeah, okay. In this case, I will send you this link. Yeah. So, but how how much are you? So like how strong is your current skill in Verilog micro architecture? So just I'm thinking.
Not very strong. I did the level 4.
So you're doing those exercises. Oh, you don't know labs, then you do homework exercises.
Yeah, I did level 4 in the homework. I was able to do this one and this one.
Okay.
But in this one, I had some trouble because in the test bench, it says -8.
Yeah.
But it's a signed 4-bit number. So
yeah, but this is still a signed number. So the meaning of signed number. Okay, so this is a saturation. Yeah, the meaning with a signed number is that when it compares signed values, like when it's compared like A minus B, it treats them as a signed numbers rather than unsigned, because minus so this is a 4-bit number, right? So 1000 is actually -8.
actually -7. I thought
No, it's a -8. So -7. So 1111 is -1, right? So 1110 -2. So let's actually get two-bit number. So let's do sign two-bit number, right? Sign two-bit number. So if you have two-bit number, so suppose we have signed two-bit numbers. So 0 is 0, 0, 1 is a 1, 1, 0 is a -2. So let's put here. So now 0, 0 is 0, 0, 1 is 1, 1, 1 is -1, and 1, 0 is a -2. You see, -1 is a 1, 1. Yeah. So like basically, if you go with a 3-bit number, so 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 0, 1, 1 is 3, but 1, 1, 1 minus 1, 1, 1, 0 minus 2, 1, 1, wait, 101 minus 3, 1, 0, 0 minus 4. Yeah. So you see, so this number, when you have only highest bit 1 and everything is 0, is actually an even number. So this is a -8 in this case. So yeah, maybe maybe you can try like exercises 1, 2, 3, 4 as well. Some of them will be like easy, but you can just do them fast and just send everything to me. And by the event you go to the 4, then I will also send you link to that example with the XI. And then you can start. Yeah, but now it's important to do that. To do this exercise, yeah. Okay, very good.
FPGAs before.
Yeah, so in this case, let's today you can try FPGA. So what kind of computer do you have? It's there. Okay. So let's so go to Verilog Meetup. Let's make sure that today you have everything to work on. Okay. So now you go this new platform. You go down. Down. Yeah, okay. So this has 3 PDF files. So go up. Okay, so you got this, and that. And I want to make experiments. So you download them, and you are trying to now to like install Glowing software. One thing. Second, to like assemble this board. Second thing, and then to run FPGA examples. Third thing. So, like, what time is? It's 1 o'clock. Okay, so you should be able to do it like within an hour. So let's start. You first install Glowing software. Yeah. So this is Windows PC. Okay, so we try clean Windows install. Okay. Uh-huh.
So what we have 168 is for what? I'm just getting out the frequency.
Okay, good. So frequency is correct. So this is a hexadecimal number.
Yep. So
number is right?
yes, there are
Excellent.
two issues. One is to get it work more or less reliably. I had to average over several cycles.
Okay.
And the second problem is there is enough noise, so it always can detect some frequency, right?
Okay.
So
But we are supposed to get video.
when I try to show the unfiltered node, you see what I expect to see, right? But when I try to filter for a node, it looks weird. For example, if you stop talking, it hangs at A because everything is changing, right? It always detects some sound.
Yeah.
So it says it's probably still A because nothing has changed. Nothing was stable so far.
Okay. Yeah. This is actually fine. This is fine.
So
This is something you can leave this.
Like, how do you want to filter the node better?
You can think about it because this is just some basic filtering we were using. So we created this. This was created actually by some Fistech student who was doing the thing. So initially I wrote this without filtering, and he created filtering. Yeah. So this is his filtering. So in his filtering, he just okay, I already forgot what was his filtering. Oh, wait, what does it fix me? Is it yours?
I commented out filtering.
Yeah. Okay.
If
So
we had the
so
same node for several cycles,
he just counts that we have the same thing for
yes.
the same thing for a number of cycles. Yeah. So you can run better filtering.
Looking for ideas. Everything that I know how to implement is too hard to implement in FPGA.
I understand. We don't have to be perfect. We need to just show one node, and we need to be able to recognize melodies using finite state machine.
So how about this? For the nodes, what you can do
For the
is,
node, if it gets stuck, it's okay. This is not like DSP and fast Fourier transform.
if we increase averaging period higher, and say average over like 1/4 of a second, then we will always have a node that kind of matches something that will update 4 times a second. But yeah, then we'll be able to completely remove the node filtering part.
But anyway, right now, I'm not concerned about quality of this demo. I'm concerned about this demo working at all. So does it actually display any node good enough to show on the show?
Like it works better than before. If I beat with a specific frequency, I see the frequency, I see the node.
Yeah, so you can see the node. But then node gets stuck.
Yes, because again, if you have noise, right? Filtering
But
always
this
filters
is
it
fine
out.
because what I'm going to do, I will bring a flute to make it fair. And I will just play flute and show that it recognizes flute notes. And flute notes are very clean.
How about this? then let me remove the filtering for the tone completely.
Okay.
And just keep the average included. So it will always show some notes, but when you play the flute, it will show the note of the flute.
You can do it this way. Okay. Just to make sure to put some like if defs, like if def old code, if def new code, put in the extra filtering if def. Okay. This is. Okay. Okay.
I'll try those examples.
So what is your next step is to try homework, right?
Yeah. Try the homework.
Okay.
Previously, I have experience on silence FPGAs.
Yeah.
So I used it using Ultra Fortis.
Yeah.
And yeah, so.
So you can continue. So do you have Xilinx FPGA board?
No, it was back in my university.
Okay. Yeah, you can learn one of these small boards for me, but the problem is that I don't know. I don't want to give them away right now because of Maker Faire. Yeah. So, but I can borrow after Maker.
Yeah,
You can borrow after Maker Faire.
Yeah,
So. Okay.
Meanwhile, I'll try the homework.
Yes. So you can now try homework. Yeah. Okay. Okay. So see. Okay. Bye. Okay.
Вопрос.
Да.
Я не могу избавиться от такого голубого кружочка.
Вот этого?
Да, то есть вот есть 3 фигуры. Вот ее даже
Да.
удалили.
И нужно сохранить файл.
Сохранить,
И
запускать.
пересинтезировать
Да, и она
не может быть. Так, Ctrl-S, сохраняем файл.
Да.
Так, и тут ничего нет. Так, хорошо, запускаем его здесь. Окей. Запускаем. Ошибка. Это просто ошибка. Так, смотрим вверх. Какая ошибка. Так, вот это вот закроем.
Вот так?
Вот он. Вот, syntax error 117 здесь syntax error. Окей. Green. Green equals 17.
Первоначально было вот такое.
Сейчас мы видим. Сейчас тут узнаем. Окей. Так, смотрим, что тут такое.
Пишет 117, 12, 14, 15. X, Y не константа.
О. This is not the constant.
Ага, это
Сейчас,
я тут
уже.
уже что-то начинала мудрить. Я хотела, чтобы он дошел до края и пошел обратно.
Так, сейчас.
Вот.
Нет, это как раз нормально. А где у него counter? Так, x. Так, просто x присвоили что-то? Ничего не понимаю. Так, syntax error laptop 117. Green. Стоп. А вы в правильной директории находитесь? И ставлю с моим бизнесом, да. Ну, вообще, этот файл компилирует или какой?
Ну вот, да, rectangle smooth.
Так. Нет, это что-то должно быть очевидно, но я его почему-то не вижу. Так, хорошо, синтекс не N. 120. Так он дальше. Все, я все понял. Тут Так, значит, begin, end. Begin пропущено. Ну, то есть можно либо тут поставить begin, либо там убрать end. Тут было пропущено begin, и так как begin пропущено, то оно просто думает, что закрывается end здесь, вот, и после чего получается syntax error. То есть тут был просто пропущен begin. Так, в counter. Нет, тут все хорошо, теперь все. Там был просто пропущен begin. Begin end, begin end, begin. Все. Все, такого нету. Да, ну, тут у меня, конечно, неправильное сообщение. Должно быть более сказано. Все. Okay, so you.
I've done a few before.
No, but right now I want you to make sure that you can work with FPGA. So this is on. Okay. So once you download, run installer, then let's make sure that you can run with FPGA. Yeah, but it's better if you just send me an email with this solution. Then you check in email, because now I want to do other people on the board. This can be done with email. Okay, now.
At least I am able to run it that directly. The point is, I am not using anymore the PowerShell. I am using the Bash.
But we need to figure out why it doesn't work with the PowerShell.
Yeah, but in the meantime, with the Bash, it's working. Here, I am running the number 9, and it's visualized with what is that? Is number 8, control using keys. This keys is supposed to be, if you press any of these keys, happens something. No, it's not happening.
What?
Yeah.
Wait, what are you trying to do?
Well, I am running the number 8. Visualize. This is what is that? It's moving. No, 7 here. Is I am using the 8.
Control using keys. Okay, so you're saying that you press key, it doesn't happen?
No, nothing happens.
First of all, is key working at all?
No, it never show anything on the 17.
Okay. The second, let's see. What configuration is this? Yeah. What? Okay, 0, 6.
Is the 52 is the one that where it is.
This looks okay. Let's see. Wrong. Okay. So what if maybe this is not connected right?
No, give us, we tested. We tested.
Oh, yep. This was just simply not.
It's not going all the way.
This command to do this command to come here. It's in this case. Now we need to make sure that we put. Okay, so green is VCC, which is red. We should connect to C. Mhm. Okay, so now let's see. Yeah, I see. So now
Yep.
it's working. Yeah, this is fine. Full electrical problem. Okay, so now you can try to modify code and to create some interesting visually pictures.
I'll hang out with these
Yeah,
guys.
okay, good. Okay, so what about you? So
I am actually doing good. I'm able to go through. I'm just trying to read up on all these the terminologies and the
Sure, sure.
books you mentioned. I got it. I started reading them. So I got a few of my, but I'm able to run the codes here. I'm playing around, modifying.
yeah, so what you can do is that I created a new directory. So if you do git pull, just do here git pull. Yeah. Yeah, it just gets a new one. Yeah. So what you can do? What you create a new directory with examples.
Yeah. Oh, the box I got from you last week is missing the potentiometer.
Oh, yes, I will give you just a moment.
Like one rainbow, there's only like 4 sections, right? It's those 4 blocks. So you take one rainbow block, do it 4 times, and then just offset 4 rectangles. Yeah. And then just offset each one. Yes, like that. Yeah. No. So
Now, so from you, I want to create new interesting color images.
Yeah, that's one of the things for me.
Yeah.
these are like
Yeah. So this one.
How do I,
Oh, just do this again because it's the internet here is not perfect.
I'll try.
Yeah. So if it fails again, I will just give you password from the like page. And oh, okay. Now, if you go into 9maker fair, yeah, just try to go through all those examples from first to the last one.
This one.
Yeah, this one. Yeah. So try try to go through like all of them, and then try to modify by yourself to create interesting pictures, especially moving. Yeah.
Unrelated off topic. Is it, if it's possible, to add at least basic frame buffer with low resolution?
Yeah.
Then it will be possible to make much more advanced innovations that you can get from 4K demos. That thing, like 4 kilobytes executed.
Yeah.
Stuff. For example, you can draw flame just by averaging like 4 pixels nearby and moving one up. That is sufficient to draw flame on the screen.
Yeah. Okay. Good. Yeah. So you can try to implement frame buffer. Frame buffer is just a flip-flop rate. You create block memory out of it.
Like how big the frame buffer can we get? Like 100 by 100? Too much?
So it's enough to make a flame on.
Like how big the frame buffer should expect?
So for each FPGA board is different.
I know.
So for some FPGA boards, they have up to like several kilobytes of flip-flop.
Let's say you're trying to make it to work on 9K, right? Because
Yeah,
it's our
on
target
9K.
audience.
You need to read how many flip-flops it can accommodate, but also it has internal block memory, which can be larger. So let's go to the website and let's see. This is a good question because I also want to create a frame buffer. Okay, 10 gram.
Yeah, well, before getting into them, how is where here in the
First of all, I still feel that if you do proper like proper I2S interface with 27 megahertz, it should recognize better.
We just did it.
Huh?
We did it. We did. So again,
You
the
need
frequency that we measure
Yeah,
is within
the
1
frequency.
hertz. Within 1 hertz.
Okay, so
It's
this
very
actually doesn't matter. But you still use the same old code as for 50 megahertz, right?
Yes, so just make sure that
but this means wait, so did you modify the code or not?
Yes, I did. Yes,
You didn't.
So
So,
the way
so
implemented
the
is,
code works.
do a divider on a frequency, and we get a frequency in between 20 to 40 kilohertz.
But so you are using frequency divider.
I'm dividing the frequency, but like
Using PLL or using
no, just straight up divider. I'm getting some frequency between 20 to 40 kilohertz, right? I can always divide by 2 to end up with in that range.
But can you show me your code?
Yes.
Okay.
Do you know what it is? I don't remember.
Yeah, yes, it's here. So where's the frequency divider? Okay, now my question is, yes, this is something you shouldn't do.
No. There are some issues there. I have to refactor the code. But
No, this is not a refactoring. This is a fundamentally wrong thing to do.
I know. You explained it today.
Yeah,
I agree with you.
Yeah, okay.
This is the point.
You need to have you need to put here clock and you need to put if.
I know. That's another for now. So I'm driving.
But the thing is that it simply gives you different samples than to like our regular design. So maybe if you get samples better, it should work better.
So I drive SCK, which is a multiple of my main frequency.
I understand. So, but the problem is that you also use negative. So this is
I don't know. I don't know. It just make it compiles, right?
Yeah, but this doesn't work well.
But you know what? No, it does. I'm checking that between 225.
The fact is that it appears to work. Just doesn't mean that it's truly exciting. If it doesn't excite,
I don't know.
it should be
That's feasible. That's nice features. They're talking about the high level thing, right? What I'm saying is I'm driving SCK at a stable top. That is a multiple in my main top.
No, that one for
Ну, тут музыка, но тут
okay. The problem is
все возможно, это долго.
there is no guarantee
Нету исхода.
for
Понятно. Задача в том, чтобы перевести текст и отдать его в голове на голову схему.
there is no guarantee for the type of your usage. Like negation, SCK, so like I can debug the thing because I don't know what kind of problems we will have.
Again, the only factor is called before we merge it. What I'm saying is, I'm driving SCK at a stable frequency. I divide the main frequency by 5 or by 9 to get the frequency within the range that random key accepts. And after that, the data that I'm getting back is tracked. I don't have any
You're
frequency issues.
absolutely 100% sure that you are getting correct data.
Again, I measured it within 1 hertz on a real hardware.
But you're saying that it glitches from that.
No. That's because there is a lot of noise, right? So you never cross the frequency also, but if you apply the peak frequency, I'm getting the exact value. It's as clean as it gets. And because I'm driving the STK at a multiple of the main frequency, it's stable. There are no issues with type issue.
So guess what?
So, yes, our question was about frame buffers.
Yeah. Let's go.
Now we get back to the STK stuff.
Now. So register. So we have 6,000 flip-flops. We have shadow memory, which is SSM 17K. So we have block RAM. So we have actually a lot of memories. You can use it as a frame buffer. The only problem is that different FPGA synthesis tools ensure different synthesis tools ensure like block memory based on your coding style. So you need to write in a specific way to like ensure block memory. And if you don't write it in a specific way, it creates memory based on registers, but you still have enough registers for a large frame buffer.
I mean,
So how large frame buffer do you want? So you want 480 by 272.
I did that.
480 multiplied 272. And
it's 130. I have 3 bits. 3 bits.
You have 3 bits, so you want to have RGB. So this is
No, 3 bits is too much. How about we'll have both of them?
so okay. So this is 50 kilobytes. So this is 50 kilobytes.
We can drive a frame buffer at half the resolution.
Yeah, you can half resolution. Okay. So you have a shadow RAM. 1 second. So we have we have 50 kilobyte. So we have 50 kilobytes. This is bits. Yeah, but here is a block RAM. We just need to figure out how to use block RAM.
What's the difference?
block RAM is some internal FPGA RAM, so it can use cells either as logic or as a block RAM. Like I'm not 100% sure how it works, but if you get the Govin manual, so ask their technical support, and we have to do this anyway. Because we have to do this anyway because we need to talk with Govin. They wanted to make a controller of a DRAM, and because they want to have a controller for DRAM, we need to figure out how to use their primitive switching for RAM. But you see, they also have SDRAM.
I'm not sure
they
about
have
using the SDRAM for a frame buffer. That may be tricky.
Okay, that's okay.
It's just a latency.
It's that's what I'm saying. It's tricky then. The code will be complicated.
So we can use a block RAM. So we just need to read the documentation how to ensure block RAM from Verilog code. So generally FPGA tools. Okay, let me show you how like it looks like. Let me get some my like old project.
And this will be true across almost all the hardware we are trying to support, right?
There are some differences in coding style, but generally
in terms of hardware, all the boards you're trying to support will have some kind of
block RAM, inference. I know this for sure for Xilinx and Altera, and for Govin, we need to figure it out for Govin. Okay, so just a second. Deep ground example.
Which part of the yellow is red 30 and green 50. One
System.
The point is you have red, green, blue, and you have what is the value. So red, green, and blue, the RGB codes.
RAM is but this is actually a controller. So yes, this is SDRAM controller. You can use it if you want to. System best сложения. Yeah, dual port RAM. Yeah, so basically, synthesis tool can look of such code and ensure block memory.
I see. And what is RAM? How do we define it?
Huh?
What's the definition of RAM on line 26?
This is just an array.
I see.
So you just define array, like two-dimensional array of bits or like array of words, and then if you follow certain template, synthesis tool say, oh, wait a second, this is block memory.
Makes sense. We are telling, hey, here is our words with, here is array of words with things, right? And then it knows, yeah, that's probably you're trying to use RAM. Make sense?
Yeah, this is like one way of doing this. So this is a second way of doing this. So the second way of doing this, we just need to make sure that this is what happened with Govin. This is something I didn't investigate before. You can investigate it now. So yeah, this is YRV plus. So second thing, many vendors, they have their own macros which allow to define such RAM explicitly. So if you go to design here, Where's my CPU? All status registers. No, this is stop. Parser. Dynamic display. Yeah, here. So yeah, so also FPGA tool vendors have some magic pseudo blocks. They provide a library which infers block memory in FPGA. So we can make a frame buffer using this method. In fact, we should do this. We just need to do such examples for sure. So you either use that template, but you need to read documentation of Govin to make sure that you infer template, or you use explicit macros.
Yeah. Okay. So all of this is doable. The buffers are big enough for sure to drive at least a half the resolution.
Big enough, yeah.
At least a half the resolution should not be an issue.
Yeah.
The only question is, what would be a good demo for a frame buffer? Because like Amiga, Nintendo, they didn't have frame buffers, and they had full-fledged games. So why would like
No, you can build a like a rudimentary GPU pipeline in principle. I'm not sure whether it fits 10 nano 9K, but it will definitely fit larger FPGA.
if we have a frame buffer, then we can take forever to actually render the picture, right?
Yeah.
We could just render one line at a time, one rectangle at a time.
We can render, we can stuff it in FIFO, and it can just get data from FIFO when it feels like it, and write it into memory. And that's it. So if you have frame buffer, in this case, we can make very efficient pipeline to write something into this frame buffer and read from it in order to like output to the screen. You can use even single port memory and ping pong scheme of read write one clock cycle.
Too hard. Too hard. Too complicated.
No, ping pong is a trivial thing. It's like I was doing it 1,000 times.
I know.
Yeah. It's actually when what many electronic companies are doing with embedded SRAM when they want to go for cheap option. But actually right now there is a pseudo dual port SRAM which in terms of area are not much larger than single port SRAM. So right now pseudo dual port SRAM is the main like SRAM to like implement everything. When you have one port for write and one port for read on every clock cycle, you can do one write and one read. It's the same.
I'm thinking that like today you are talking about that, hey, we need to build something that is more like tangible, right? It's not just, hey, I can compile the CPU, good for you, right? And when I'm looking back,
no, for frame buffer, I was planning to make a demo with frame buffer for a long time, for like years. Just I never had enough time to do this. So yeah, we can create a demo with a frame buffer. And if 10 nano 9K is not enough, we have 10 nano 138K.
It will be enough. It's always possible to drive the demo on any kind of hardware, right? Just be low resolution. Yeah, I wonder if the games will be a good thing to do. Like, say, Amiga, they only support like sprites of the whole line.
Don't really want to appeal to
It's easy to explain how things are, just going through
No, this
iterations.
is to explain to their roles, because they were doing it for them this is cool. But for now 20-year-old, they don't care, they don't care about this shit. This is the, and if you tell the look, this is great.
No, not actually. Here is how Amigo works, but
Get the joke,
uh,
like up for a or something.
incrementally more complicated examples.
I think we need to figure out something. If you want to do Amiga games, you need to implement
No.
something stuff.
As soon as you say not the real games, not the real Amiga.
Yeah,
it's
but,
just-
but you know, like you want the games in the same style.
Yeah.
Yeah, and so games is like scrolling with some, is like scrolling area and some moving and shooting something. Yeah, you can make such games.
Maybe just go directly to Nintendo. Just maybe skip Amiga, go to Nintendo like you do right now, right? You have a few sprites.
Yeah, those a good idea of those spreads from the sex games I was playing in 1985. There were some Japanese MSX Yamaha computer shipped to Soviet Union, but the government authorization for. I was one of those lucky people who was exposed to Texas Instruments video processor, which was used for those games. Yeah, and yet that video processor had sprites. So I created software sprites when I was 15 years old. And like this was cool.
That's really cool.
And so and same thing is easy to implement Verilog. But now if you want to make some nice background for it, you can implement frame buffer. But you see, like in MSX, they didn't have frame buffer for every dot. They actually put most of games in a text mode, but in a very weird text mode. There was a special text mode where you can have each character
Yes, each 8
to
by
be
8.
a multi-color object. Then they created screen out of such characters and knew that this was full graphic screen with like many colors. Plus, this mode also allowed sprites. So most of games were just like moving. So nobody even thought text. This was actually text content. It's just each character was a multicolor graphical object.
Or if we are running low on memory, we can use similar thing to what ZX Spectrum was using. Bit mask plus 2 colors for each 8 by 8.
Yeah, or like you can make a perception of this like word table of such pseudo characters. Then instead of trying to make a 300 pixel frame buffer, all we have to do is to make 40 by 25 character screen with such pseudo characters.
Yeah.
And this creates an excellent scene. Yeah, but the number one priority is just to see how far we can go with such with such simple. Окей. Хорошо, тогда сейчас нужно подкрепить, нужно для всех билет. Сейчас я это
Один на один день. Sunday.
But make sure to make a git just
It can be by then by mail, by. Если сегодня воскресенье. $100. Это не заплатил.
Just make sure to do select by
Смотри, я сколько тебе наплатил. Вот.
Okay. Okay, so where you're able to download the message. Oh, wait, did you load the commercial version? I did, then release it. So you have education, it's been installed. And you do the requirements. But I don't know. Yeah, just a second. Then you need to follow second instruction. So you need to, okay, so, yeah, this one I will give you like already a sample. So you need to give another instruction called run. Yeah, so this one I will give you.
Потом если посмотреть, где купить.
Now,
Пересекается.
instruction.
Ты можешь выбрать это бесплатный маршрут. Ну, я должен ехать подойти. Ну, то, что сверху, ты можешь там через это ж тут и поверху можно вот через окно.
You can actually right mouse. Open it. So now what you do is you press the brush and use this. Opa, you have Windows system Linux. Okay, in this case, what you do is you need to yeah, that's all. Just if you complete.
Нет, на Windows дает подсистему Linux.
Let's just open Bash. Bash.
Пакет программы.
Timothy, how to open Bash terminal?
Bash terminal, there is near the plus sign, there is a triangle there. LJ. Near the plus sign, there is a triangle. Yep. And here you can click the debug. It should be documented on the
Why doesn't that a regular or shelter? This is strange. Maybe just got splashed from Windows system projects. Oh, it's not in your pass. When you store, you just put bash into your pass.
Okay. The path.
Yeah. If you follow instruction, so let's actually follow. So did you read instruction? That's so you can download bash for Windows and then the PDF command to check the use bit adoption by Unix tools. So you need to check it. But if you didn't check it, so you probably didn't check it.
Back to the next for that.
Okay, this is fine. So what we can do now, you can just use bash terminal in this case, which is not. So let's go back here. That's very easy. So now let's no. You're not in the right page. You need to go to labs. Go to the let's actually go to Meetup. We'll go to the night maker. So this is so slow. Maybe you can install Git for Windows. Хорошо, значит так. Прежде всего, сколько вы можете там находиться? Можете ли вы там находиться все эти дня или столько один день? Что вообще? Но туда ехать достаточно далеко. Все равно можно снять забор. То есть это не что. Но вы кто туда ехать?
Ну, да это будет или больше.
Я точно не знаю. Ну, часто нам точно. Часто. Ну, хорошо. Тогда, значит, можно делать. Я туда приезжаю сам в четверг, где останавливаюсь в отеле. Вот, после чего я туда прихожу утром. Вот, расставляю там, если вы туда тогда приезжайте, как можно рано. Нужно посмотреть, какое начинается 10 дней. То есть, если вы туда приедете в 9, где-то так, там уже потом. Я думаю, если вы туда приедете в 9, то там уже походу делать больше. А ну, заканчивается часов. Да.
если не с сверху, то есть примерно полутора с 10 до 5, что ли, потому что ничего такого особо нет, там, если нужно обойтись, там, если я там, да, то есть нужно, по сути, приехать, но я тоже, что тяга, все, больше вот сможет сказать. Я ну, хорошо, значит, там, значит, распечатать постер, там, сейчас. То есть просто вот берете, приезжаете, там, как раз берете. Так что. Okay, so now. Now, choose a point, just 90 years. That another man paid us 348 to 72 years system based on search. So this is 50. Around sometimes sometimes you just need to use helps. The camera helps, so this doesn't work. The camera help. Let's USB to solve. Now it is 0, 4. Okay, now the goal for today is so you want to which one? You want to restrict rectangles moving using parts. Is to make some text. So get some rectangles, get circle, so just look at how whole thing looks like. So there are some counters. So yeah, you can also watch some examples of the or you can go to this rectangle parabola and see how it all looks. So just to try to build something visually, try to build some patterns, moving parts. And if you create something interesting, shoot me email, I will show it later. So do you plan to go to Maker Fair? Yeah, so now let me get this, see how many tickets I can get with them. Yeah, so ticket, okay, 1, 2, 3, 4, okay, so let's get tickets for like everybody. Вам нужны еще билеты для вашей семьи? Что есть некоторое количество дисконтных билетов, то есть можно на них тоже взять, если у него в месяц количество. Давайте посмотрим, сколько я могу взять. И это вот. Okay, so let's get tickets as much as we can. So this.